Hello, today is the last day of word problems. Now, this is the trickiest day, so I'm going to try to be as consistent as I can when I teach these problems. These are distance, rate, time problems. Okay, there's three types of problems. There's distance covered two different ways, catching up or chasing each other, and meeting in the middle problems. Okay, let's just go ahead and get started, and I want you to just notice a pattern as we go ahead and do all types of problems. All right, first thing we're going to do, every single problem, once you recognize it's a distance, rate, time problem, we are going to make our distance, rate, time chart. So I like to do rate times time equals distance. So Jeff can bike to work in 3/4 of an hour. So taking the bike takes him 3/4 of an hour. By the bus, the trip takes 1/4 of an hour. So bus is 1/4 of an hour. If the bus travels 20 miles per hour faster than Jeff rides his bike, how far is it to work? So what usually happens is either your rate or your time becomes your variable. So I'm going to use K for bike and S for bus. Now, how do I get the distance? Distance equals rate times time. So multiply the rate times the time. So 3/4 K and 1/4 S. Now, use this information, use the other part of the problem that we didn't acknowledge, and write your two equations. So, he either rides his bike to work or he takes the bus to work. No matter how he gets to work, it's the same distance. So I know these two distances are equal. Now, what is the one thing I didn't talk about? I didn't talk about the 20 miles per hour faster. So it's 20 miles per hour faster when he takes the bus. So I know that the bus is going to be his walking rate plus 20 miles per hour faster. So that's what we need to think about. Now we have a simple substitution problem. We're going to go ahead, take this, plug it in for S. We get 3/4 K equals 1/4 K plus 5. How did I get 5? I distributed the 1/4 to K and to 20. Then we go ahead and solve. We get 2/4 K equals 5. 2/4 is the same as 1/2. Multiply by 2. Our K is 10. Now what did we solve for? We solved for the bike's rate. This is K. Now let's read the question. It says, how far is it to work? So right now I don't know how far it is to work. I just answered the rate on the bike. So what do I need to look at? I need to look at the distance. So 3/4 times K, so 3/4 times 10 is 7.5 miles. Now be careful, because the reason these problems are so difficult is because I could have done the same exact word problem but then said, how fast does the bus travel? And then you would have had to plug it into somewhere different, okay? All right, let's just go ahead and go on with the next one, and I'm hoping that you recognize a pattern. Let's go ahead and set up our distance, rate, time graph. Chart, I should say. Rate times time equals distance. All right, Elaine, we'll use E, begins jogging at 5 a.m., averaging 3 miles per hour. So this time we know her rate. Clay leaves at 5:30 a.m., following her, averaging 5 miles per hour. How long will it take him to catch up to her? Well, look at the rate and look at the time. We know the rates. We don't know the time. That becomes our variable. Again, our distances are going to be rate times time. So 3E and 5C. Now, what's happening with the distance? Are the distances different, or are they the same? They are the same, right? Because they just leave at different times, running different speeds. They're still traveling the same distance. So in this problem, we can go ahead and set our distances equal again. Now, what didn't we take into account reading this problem? We didn't take into account the difference in the time. So we know that Clay leaves a half hour later. So I can take Clay, set it equal to Elaine minus 0.5, or a half. I just put it in decimal. I thought it's a little bit easier to see. So now again, I'm going to solve this problem by substitution. So I get 3E equals, I'm going to take 5 and distribute it to E and 0.5. So we get 5E minus 2.5. I'm going to go ahead and move the E over. I get negative 2E equals negative 2.5. Divide both sides by 2, and I get E to be 1.25. Now, we have to think about what did I just solve for and what am I asking you for. So I solved for Elaine's time. So Elaine must be running 1.25 hours. I asked you for how long will it take him to catch up to her. So I'm asking you for Clay's time. In order to get Clay's time, I need to solve for C. So I'm going to take my E and plug it back into here. So Clay is going to be 1.25 minus 0.5, which gives me 0.75. Now, we don't really talk like this. I would accept this answer, but we don't say, oh, I went running for 0.75 of an hour. What is 0.75 of an hour? Well, 0.75 of an hour, if there are 60 minutes in an hour, I take 0.75 times 60, and I get 45 minutes. So Clay has been running for 45 minutes. And if you write 0.75 of an hour, I'm okay with that too. All right, let's go ahead and try another example. This one is a meeting in the middle problem. We are still going to do our distance, rate, time chart. Rate times time. Notice my chart is the same every single time. Johnny leaves Memphis to visit his cousin, Ann Hoffman, in the town of Hornsby, Tennessee, 80 miles away. He travels at an average speed, so this is Johnny. He's traveling at an average speed of 50 miles per hour. A half hour later, Ann leaves Hornsby to visit Johnny. She travels at an average speed of 60 miles per hour. How long after Ann leaves will it be before they meet? So I have the rates, which means I don't have the times. That's where our variables go. Our distance is going to be 50J and 60A. Now this one's a little bit different. They're in two different towns and they're meeting in the middle. So they're 80 miles apart. So instead of their distances being equal, I know that their distances must add up to be 80. That's our first equation. Now what didn't I take into account? The half hour later. That again. So if I take a look, I know that Ann is going to be Johnny's time minus a half hour. And again, is it okay if we had J equals A plus 0.5? Of course, because Ann is traveling Johnny's traveling a half hour more. Either one, okay? Take this, solve by substitution. When you go ahead and solve this, I'm not going to do all the math here, we get J to be 1. Now, what did we just answer? We answered how long Johnny's been on the road. What's the question asked? How long after Ann leaves will it be before they meet? So I don't want Johnny's time, I want Ann's time. So I need to plug this back in and get A. So A equals 1 minus 0.5, which is 0.5. So it will be a half hour, or half hour is the same as 30 minutes. Either one of these. Okay, so a lot going on here. Basically, if you're consistent with the way I'm doing the problem, we're going to set up our distance, rate, time chart. You're either going to have numbers in the R column or numbers in the T column, one of those. Whichever one you don't have, you put a variable, and then we look at what equations we have. What's going to be our distance? Are they going to be equal? Are they going to add up to be something? And what's the difference? And usually our time, not always. And then, of course, you have to be careful to answer the question correctly. Let me just help you get started on this problem, just making a chart, and then I want you to try writing the equations yourself and solving the problem. So we have Jose left the White House and drove toward the recycling plant at an average speed of 40 kilometers per hour. Rob left an hour later driving the same direction at an average speed of 48 kilometers per hour. How long did Jose drive before Rob caught up to him? So we have our time is our variables, which means we know what we plug in for the distance column. And I want you to try to make the two equations and solve. One has to do with the distances and one has to do with the time because Rob left an hour later than Jose. Okay, questions, comments, or concerns, go ahead, write it on the bottom of the paper, and I will see you tomorrow in class.